We're assuming here that the target type is a monoid, so you can imagine this is the empty list of bits. And here, if there's a bit on the head of the word, I'm going to format the rest of the word, and then I'm going to use this SNOC operator, which is provided by this monoid, to stick that bit on the end. So what's going on here is that the word encoding we're using here is actually little endian, and the network format is big endian, so we have to do this switcheroo, but it's not too bad. And then on the decoder, we're going to invert the process. It's going to use an unfold operator to peel the bit that's on the front of the target data type off, and then reconstruct the original word. So we don't need to worry too much about how these bit level operations are working, but sort of the cool thing to note here is that hopefully you can read these functions. They look very functional, and the Narcissus specific details that we'll be getting to in a little bit are actually nicely hidden in this monadic bind operation notation, which is great. So maybe you could even imagine writing such one of these functions. Of course, you might say it's easy to write functional programs. Maybe proofs are a little bit harder. How do we write these proof components? Well, proof components are proofs, and you have to write the proofs. So, and you're going to fire up, your interactive cock buffer and your write a lemma relating these two things, these two functions you've defined, and the difficulty you have, proving these inverses is directly related to how complicated this format and the decoding of this format are. So, you don't get the proofs for free, unfortunately, yet. Okay, so here's another tweak or another cool feature of Narcissus that is going to get back to that question that was asked some time ago. So here's the thing about standard binary formats that you may not know. It turns out that many formats do not prescribe a canonical target representation for a given source value. So what does that mean? Here's an example, and I'll give you more real examples in a second. So suppose we add a new version field to this format, because that's the thing to do, and our standard is going to prescribe that the lowest two bits of this field are going to be 1, and the rest of this version field, I don't care what it is, and in fact, you don't even need to reflect it in the source data type. It doesn't matter. Well, it turns out now that there are 2 to the 6 different encodings for any source value for a simple record type, right? We could make this all zeros, you make it 1 0 and 5 ones, so on and so forth, you can imagine. And you can do the math, and hopefully it adds up to the 6th. Okay, well, this seems a little bit silly, and why would anyone want to do this? Well, it turns out, of course, that people are silly, and when they standardize things, they do silly things. So as an example, one of my favorite examples is actually the Ethernet header standard. For some reason, there were 2 different formats floating around for a while, and to standardize them, they just took them and they glued them together, and they said it could either be this one or that one, and there's this magic field that you look at in the format, and if it's above 1501, it's going to be this version. If it's the other one, it's going to be this version. Why not? And that's the standard. So one way to develop standards is to glue things together randomly. Why not? ASN.1, which is a data description language, for some reason, has multiple different encoding rules for a given data type, and their original one prescribed different ways of encoding numerals, among other things. So they actually devised another set of encoding rules that had canonical forms, and then there are a bunch more on top of that. But DNS is a weird one. It has an optional compression strategy. So whenever you encode a domain name as a binary string, it's completely, you can choose to encode it as just the string representation, or you could encode it as a pointer back to a previous encoding of that same domain name, or you could do several things in between. So it's rather complicated. And even to this day, standards like Google's protobufs will allow you to encode many different encodings of a given source value for maximum flexibility. So what's the take-home message here? The take-home message here is that a decoder, there's no longer a strict bijective relationship between the source value and the target value, right? So our decoders they need to recognize all of the possible encodings of a source value, and they need to correctly recover the original source value, however it was encoded, as long as it sort of fell into its original set. And we need some way of actually specifying what the possible ways of encoding a source value are here in the format. So what's our solution? Our solution is that instead of representing formats as functions, we're actually going to give them a relational interpretation, which means that a particular format is going to relate, it's a binary relation that relates every source value to a set of potential valid targeted values, including the empty set. So there might not be any encoding of a particular source value for some reason. And so what's nice here is that this actually, we can actually, once we have this relational representation of formats, we can define a choice operator that you can basically read as, give me any value satisfying some predicate P, and we can encode this version magic number here is, I'm going to encode a word, and that word is just going to be anything that's greater than 110000, greater than or equal to that. And now this format precisely captures all of the possible encodings of a particular source value in a single definition. Okay. And now we sort of reviewed all of the features of Narcissus specification, high-level features I want to talk about. What's nice here is that this framework is completely open, right? You're completely free to define your own format specifications or combinators, and they'll integrate nicely. As long as you write the proof showing that your particular component is correct, you can include it in some larger format, and assuming you have the right set of proofs, you can glue everything together with existing components and prove some novel format is incorrect. So as an example, you might decide to write down a combinator for IP checksums, which is a combinator that isn't used very often, but you can do that. And then you can easily and hopefully legibly write down the format for IPv4, which is pretty sweet. Okay. So this is just a high-level overview of what we can do in Narcissus. And now I'm going to take an interlude before I dive into more details with a couple of my favorite quotes about writing software. Of course, they reflect the worldview of famous computer scientists who agree with the value of verification. So the first of these is from Tony Hoare. And so when Tony Hoare was writing up his Turing Award-winning lecture, he was reflecting back on his long career, and he has this great quote about how to write software, correct software, or well, how to write software. There are two answers. There's one way is you can make it so simple that there are obviously no deficiencies. And the other way you can write software is to make it so complicated that there are no obvious deficiencies, right? Which is a little tongue-in-cheek. This was referring to the design of Algol 67, maybe, which I guess he didn't completely agree with. What? 68? Thank you, yeah. But so what's nice about what we've done here is that these, and in fact, a deep spec in general, is now we can have arbitrarily complex software, and you can believe me that these encoder and decoder functions you synthesize are a little gross, and you can imagine CompCert's implementation is rather gross. And I won't say that Certicos's implementation is particularly gross, but the specification is so simple that it's easier to audit and convince yourself and ostensibly test in order to convince yourself that the specification, the part you actually have to trust, is correct. And so that's why this approach to synthesizing software from specifications, you don't have to trust that the synthesizer is correct as a user. You just have to trust that you wrote the specification down correctly, and then the code you get generated is correct by construction. Okay, so another quote from a famous computer scientist, a little bit more, what is the word for it? Prickly than Tony Hoare is this great quote from Edsger Dijkstra from '67. And he was sort of bemoaning the state of software development in 1967. And he was talking about how people would just write down pieces of code and then they would test it to make sure it was right? And there's this great line in this paper where he was basically describing this approach to deriving correct programs. He didn't call it deductive synthesis, but he was arguing you take a specification and you derive a correct implementation from it. He didn't know anything about Cockit, obviously, but this is sort of realization of that dream. Anyway, towards the end, he ends with this stinger in 1967. He said, personally, he felt that debugging and testing was invented by shortcomings of programmers and people writing programs this old way. And pretty soon, people would be writing software just by driving it where it was obviously correct, right? And this was going to be how we were going to write software in the near future in 1967. And I'm happy to say that 50 years later, we're getting closer, at least for some pieces of software. Okay.
Well.
Uh-oh.
At least half right.
Yeah.
Long ago, we denounced it as obsolete.
Fair enough. It was obsolete 50 years ago, and it remains that way today. So anyway, okay. So just to recap, sort of high-level design decisions that we made in Narcissus, which make it convenient for specifying these binary formats. So one, we have non-deterministic relational formats, which allow you to encode these standard binary formats where there are many different ways of sticking a piece of source data on the wire. And nicely, the Narcissus-specific details are hidden in this monad notation. We'll see some of those details in a second. We advocate a combinator library approach for decoders and encoders. I'll get to that parenthetical aside in a second. That is keyed on a common format that specifies, this relationally specifies how things can appear on the wire. I'm arguing that we can automate these derivations when possible using tactics. If you remember from that example derivation I showed, you could imagine having a tactic that automatically applies lemmas or proof rules that are drawn from a hint database. And indeed, that's what happens under the hood. And then finally, what's really nice about this style is that we can represent dependencies between some formats, and they're reflected in the proofs of correctness for the individual combinators. What does this mean? This means we can capture non-context-free formats in Narcissus, which is just necessary if we want to do anything with these standard binary formats, because most of them are context-dependent. So threading this proof, these facts through about what you've seen before is absolutely necessary if you want to verify these standard formats in a compositional way. Okay. Are there any questions about the high-level story? Yes?
Are there any restrictions on the predicates you can use to filter out?
Indeed, there are not. You can actually put an arbitrary predicate in Narcissus. You could include an arbitrary source restriction, which means ultimately that you need to be a little careful about what you put in there, because you could put some undecidable predicate in there, and the decoder should be able to you could get a decision procedure for such an undecidable predicate if this worked. Of course, when you try and write the proof or you try and synthesize an implementation of such a decoder, you're going to get into a problem, because Coq is probably not going to certify that you've come up with such a decision procedure. Yeah. So, indeed. One of the downsides of being so flexible is that it is possible to extend the specification language in an unsafe way, in the sense that it might not be possible to synthesize an implementation. Yep.
So how complicated can these predicates get in the real world?
In the real world, actually, and they're not too bad. I'll put it that way. I think generally think about it this way. If you had some crazy, complicated restriction on source values, the chances that anyone would get that correct are very, very small. Of course, you could argue that if you were trying to synthesize a PDF, something for the PDF format, no one's gotten that right, so maybe that has some sort of undecidable restriction. But yeah, for the sort of the standard network protocols that you see, these things tend to be decidable. Yeah. Yes?
Suppose you have an Ethernet driver, but the other party might not be punctual about following the standard. What happens then?
Okay. So the question was, if you're communicating with someone who's not very good about following the standard, what will happen, right? And let's get on to the details, and I'll spell out exactly what happens. Sound good? Okay. So just as a beginner, let's draw back the hood, or pull back the hood, or whatever the right phrase is, on what exactly formats look like. So recall I had this format in type alias before type level definition. what does that actually expand to? Well, in Coq, it's going to correspond to a set of A. So for a set of, should actually be ensemble if you're a Coq aficionado, but you can just assume it's a set, as you might expect, of some source value, some target type, and we're also going to have some state. So all of these formats are going to live inside the state monad. It turns out this is convenient for sort of wacky formats like DNS. Again, that's all hidden under the monad notation, so if you don't use it, you don't really care. Okay, so one of the nice things about having this defining things as sets is it turns out that this set ensembles actually form a monad, the non-determinism monad, and we can define set level operations in terms of the standard monad, the monad operations in terms of set. So returns a singleton set, bind picks some value, if you will, out of the set you're binding from, and then returns this set former function on that particular value. So it sort of composes sets together, as you probably expect. And then finally, we have this choice operator that's specific to this monad that I mentioned before, and it's just inhabited by all of the values that satisfy some defining predicate P. So we can use this to define our base formats, or we can actually define our own higher level formats. And so Narcissus has some built in by default. So we have like a sequence format, which is defined perhaps as you might expect, where you take two subformats. You format the source value according to the first one. You format the piece of the source value according to the second one, and you sort of glue the results together using the monoid operation. There's a compose operator here that allows us to do projection in general and also restriction. I won't get into details. And then there's a union format, which is defined as you might expect. It says this is inhabited by any element, any set of source, starting state, target value, and ending state that is included in one of these formats that are included in the union. And this is the way you can have these sort of these varying formats. Does that make sense? So pretty, hopefully standard specifications with an intuitive sort of elementary semantics. If you know set theory, you can probably read and understand what these things mean, I hope. Okay, so given that formats, there is one problem, one wrinkle. Remember I said before we had to imagine that we could interpret formats as functions, right? Of course, these are not functions, they're relations. And if we actually want to encode a piece of data, well, we probably need to turn that into an executable function somehow. And indeed, there is an extra step in Narcissus. We actually provides a way to synthesize an encoder from a format specification. And what is an encoder? Well, it again is, we define it using this type alias, and it's just a function from source value, starting state, to potentially to some, well, an option type that includes a target value and an ending state. Why is it an option type? Well, recall that these formats could have restrictions on them, and I said earlier that some source value might not have any encoding, right? So if you try and encode a source value that's not included in the relation, we signal that that's problematic with none. And so what is the correctness criterion for a correct encoder? Well, it just says that if you try and map any source value using this function, it should end up in the set of valid target values that's defined by our format, which is represented graphically using my poor illustrative powers here, or we could represent it using math, and we can also just specify it using in Coq is the following set of predicates, namely, if you encode a source value and you get a target value, well, that better be included in the format. And if you encode something and it doesn't map to none, it maps to none, then it must be the case that there are no valid target values that are included in the format. So pretty intuitive specification of encoder correctness here. On to your question, what does it mean for a decoder to be correct? Well, there are two ways to do this. One approach, well, let me say what we do. So what we say is a correct decoder is one that maps every possible target value that's in the image of some source value back to the